The only other downfall is it doesn't actually show me like it's recording. I just have to kind of trust that it is. So as we kind of go into this last group, one of the things that you'll notice is a lot of the last group are asking for a velocity. Like this one talks about in number 30, this quarterback is throwing a football, and it's kind of a weird question. They just say to evaluate this claim, determine the speed with which the quarterback must throw the ball. So they want you to find the speed they're actually going to throw it. In 32, they talk about finding the launch speed. In 68, it says how thick is the magazine. So this one's a little bit different. We're going to try to find a thickness. And then 70, like I said, 70 and 32 are very similar to each other. And you're also trying to find a launch speed. So this is a little bit different. We haven't been finding speeds before. All the other problems up here have always given us how fast something is going. Now we've got something slightly different. So I'll start with number 30. It says this quarterback claims that he can throw a football a horizontal distance of 183 meters. That's 200 yards. In other words, he can throw it 2 football fields. Crazy claim. I've watched NFL in the past. If you've ever watched the old Pro Bowl down in Hawaii, and they'll usually do different tests, and one of them I remember is they were doing distance, like who could throw it the farthest, and a few years ago when I watched it, they were throwing it at a max somewhere around 70 yards. So to say 200 yards, that's crazy. The other thing they mentioned is he throws it at a low angle of 30 degrees. And I'm like, well, that seems really weird, because actually the best angle should be 45. And if you really want to get distance, you'd probably tilt it maybe closer to around 40 to kind of account for the wind. So I can't imagine you would do it at 30. And so what we're going to try to do is figure out this speed. So I'm just going to grab number 30 here, get some space. Dude, there's a good spot. So we can draw this out. So there's our path. Get our football player here. He's going to throw his football. There's our football. So the idea is he's going to throw diagonally. This time I don't know what VI is, so this is what I'm going to try to find, but I do know the angle is 30 degrees. So the idea is he's going to throw the football. It's going to travel through its nice little parabolic path and land somewhere over here. I'm going to kind of ignore the little bit of distance for his height compared to how far he's thrown it, because theoretically he says he can throw it a horizontal displacement of 183 meters. That's 200 yards. 200 yards compared to how high off the ground I'm throwing it, that's negligible, because I'm throwing it maybe 4 or 5 feet off of the ground when I throw it. I suppose if he's really tall, he might be closer to 5 or 6, but pretty negligible compared to this, because you're talking about under 2 meters. So if I do that, how do I go about finding this VI? Well, in this particular problem, one of the things that you could always do, what I've been doing, is I've been saying, hey, let's break his velocity into a horizontal and a vertical. But I did that when I actually knew what VI was. I don't actually have VI, so those aren't really going to help me very much. Instead, what I'm doing is, this is the reason why I created that little equation that's at the bottom of the combination. I've used it a couple of times, but this equation down here, there was a reason why I created this one down here, is so that I could actually solve some stuff. So I want to very briefly explain where that equation came from. It was in the video notes, but it's been a while, so I just want to kind of explain it again, because that's what I'm going to end up using. Really what I was doing is, I know that normally to find Vx, I have to take Vx and multiply by time. And then this would be the total time in the air. Well, the total time in the air, we haven't actually been finding that. What we've been doing is having the football or the object go up to the peak, and we say, hey, we know what Vy is up there. It's 0 at the top. So if I find the time it takes to go up, the time to come down should be the same, so I could just double that. So my total time in the air, is actually equal to 2 times the time it takes to go up. And then the way we found how much time it took to go up is I actually borrowed this equation. I took the VFy equals VIy minus g times t. And I said, hey, VF is going to be 0. So these two would equal each other. And so I've got a neat little way of finding the time it takes to go up. It was just equal to VIy times g. So we've kind of been using this. It's not really specifically on our equation sheet, but you almost can put it on there. I feel like I've been using it over and over and over again if you want to use that. So the total time in the air, is actually just going to equal twice this. So I'm going to 2 VIy over g. So here's where that equation actually came from. What I did is I took this concept and I substituted it into this to create one big equation. So to kind of show that, it's saying that x would equal Vx, but then for the time in the air, it's going to be that stuff. So you don't have to do this when you solve a problem like this. I'm just showing you, I'm just reminding you where this equation came from. Ta-da! I have a little equation. You go, okay, that's fine, but how does it get me to VI? I want VI. I don't want VIX or VIY. I have way too many unknowns in here. Well, then we have to kind of borrow how I actually find things like Vx. Vx is actually your Vi times the cosine of theta. So if I take that and substitute that in here, this is going to be, I'm actually going to switch it over to red so you can kind of understand that now I'm moving with my red stuff. So this is Vi times the cosine of theta. That's what Vx is. And then VIY is normally found by taking your Vi and multiplying by the sine of theta. So if I replace that over there, so I've got 2 times Vi times the sine of theta. All of that is divided by g. And ta-da! I have created the equation that we had from before. Great little equation when you're trying to find how fast you have to throw something to go a certain displacement. The only requirement, however, is it has to start and finish in basically the same height. In other words, we have to really ignore this little bit of height here, or say that he throws the football to a receiver who catches it 200 yards away at the same height that he threw it from. So this doesn't work if you were, say, on top of a building and throwing it down into a valley, or if you were down on the ground and throwing it up on top of a building. It doesn't work. It's a little more complicated. Not too bad, but it's a little more complicated. Now, like this, you're like, how am I supposed to get VI? Well, we realize we got VI and VI. They're both the same. I can multiply them together and then kind of bring everything else to the other side. So that's basically what we did. Is I'm going to take this equation and let's move it to red. So I'm going to write it up here so you can kind of see it. So if you want to find the initial velocity, basically that would be VI and times VI. I'm going to bring those together. So I got VI squared. And then I'm going to bring everything else to the other side. The first thing I'm going to do is I'm going to take the g and multiply by the x. So on the right side, I'm going to have, that's the wrong color, bring you over here. Then I don't have to reach across. I'm going to take my g and multiply it by the x. Those are the two things that are going to be on the numerator. And then I have cosine on the bottom, I have sine on the bottom, and I've got 2 on the bottom. So we've got, I always put the 2 in front. 2 times cosine, then times sine. But that's what VI squared is, because that's VI times VI, so I just want VI all by itself, so I'm going to end up square rooting that whole thing. If you want to, you could write this as a separate one. This is the same equation that I have down at the bottom of that combination. It's the same as this one. It's a way of now solving for VI instead of solving for X. So neat little equation. If you know how far something goes and the angle you launched it, you can find about how fast you launched it. When you actually find this out, you will find out he needs to throw this football at more than 100 miles per hour. When I was researching a few years ago when we were doing this problem, I found out that footballs don't get thrown at over 100 miles per hour. Baseballs can get thrown at over 100 miles per hour, not footballs. And typically footballs can get up to like 60 miles per hour, and that's a really good arm. So to say you could throw oh yeah, I just have to throw it 105 miles per hour and I can get it to go 200 yards. Plus, that's ignoring air resistance. Is there air resistance on a football? Well, duh, of course there is. So there's no way he'd be able to throw this. You couldn't even put it in something to launch it. So the other one that made me think of this is baseball or softball. Ever had like a pitching machine? One of those little wheels, and you drop the ball in and it just launches it for you. I've seen those with footballs as well, where it's basically a couple of wheels and it'll flick it like that. The hard part about it is if you play around with a football, you know the best way to actually throw a football is you got to give it spin. That helps keep it kind of straight. So those will toss them really nicely, but they don't give them quite the same spin. So even a launching machine I don't think would give you a good setup. Ta-da! Problem number 30. This is a good one to kind of keep in the back pocket because this concept, this idea is a useful one of, okay, we've been finding how far something goes or how high it goes or how long it's in the air. Now we're kind of reversing. A lot of times you don't know how fast it's launched at, but using all that same information we've been doing, things like this equation for finding the time in the air and this equation for finding how far it goes, we've kind of reversed back to finding a neat way of finding velocity. So that's kind of led you to the ledge. You just have to finish it out. Oh, just to make sure, it's not usually a big deal, but just kind of a couple of things. When you're doing this bottom, I usually do put parentheses around the whole thing. Just that way I know that I have to multiply all those before I do the division. Just realize your calculators are stupid, and sometimes when you start dividing they just don't realize you want everything in the numerator or everything in the denominator, so just kind of watch out for that. There is actually a way to modify this equation so you could solve for an angle. We're not going to do it just because I know everybody in here isn't quite at the same trig level to kind of understand it, and I don't want to throw something at you that you've never seen. But if you get into some upper level trig, you'll actually start talking about trig identities, and trig identities is actually, this is one of the places where that's useful. Okay, let's move it on. Oh, yeah, put it over there. Now I have to go all the way over here to go backwards. Next up, 32. So 32 says the highest barrier that a projectile can clear is 13.5 meters when the projectile is launched at a 15-degree angle above the horizontal. What is the projectile's launch speed? So in other words, you're trying to launch it over something. So now we've got a height that we're going after, and we're trying to figure out what angle or what speed I need to do to launch it. Matt, you've probably done something similar to this. You're like, hey, I want to throw it over the fence or over this wall. Or I remember as a kid, I always tried to throw things over the house. And sometimes I succeeded, sometimes I didn't. But that's kind of the idea, is how fast do you actually have to launch it to get it to go over that distance. Notice I don't really care about how far horizontally it's going, which is one of the things I get thrown off, but I'm going to use that 13.5 to kind of figure this out. So, problem number 32. Let's see if we can get a nice little setup. So I have some barrier here. I don't know what it is, so I'll just make it a wall. It's in the way. And they say that this is 13.5 meters tall. I'm going to make it in green because I know it's some kind of vertical information. We'll see where we're kind of going with it. I don't really know. It just says a projectile, so I don't know how to do this. So I'm just going to have a person kind of throwing something. So let's just have them throwing some kind of ball. That'll work. Well, baseball. There we go. And they're going to launch it. And all we know in this problem is they're going to throw it at a 15-degree angle. So the idea is we want it to travel in its parabolic path. Oop, it's not going to make it over that barrier, is it? I'm going to shrink this barrier a little bit. There you go. That's actually 13.5. I was just tricking you. So we're going to throw it. It's going to go over this barrier and land somewhere over there. So what we're trying to figure out is how fast do you have to actually throw it so that will happen. Now I'm going to do it so that we're going to kind of ignore the thickness of the ball and the thickness of the barrier, so that I want this thing to just barely make it over. So the idea is it's basically going to be right there on top of this thing. So when it makes it, it's just barely making it over. Maybe tipping it just a little bit. So when I do that, a couple of things that we know is where does this person need to be so that happens? Well, they need to be at the point where this is at the highest point. This needs to be at the top. Wait a second, we've been using the top all this time. What do I know about the top? I know the velocity is going to be 0. So here's how we're going to go after this one, is we're not actually going to find VI directly. Let's go after VIY. The reason why I want to go after VIY is look so far. I already have one velocity. I have a vertical velocity of 0. 13.5 is technically how high this thing is going to go. It's how far vertically this thing is going to go. What else is acting vertically? We know gravity. Good old 9.8. So here instead, I'm going to go after this problem a little bit differently. I'm going to figure out what VIY is. Let's figure out how fast vertically he has to throw this ball upward. So when I do that, I'm going to use just green stuff. So I need an equation that doesn't have time in it. And the one that doesn't have time in it is this one. The fact that VFY squared equals VIY squared minus 2 times G times Y. So this one is what I'm going to use, and this time what I'm going to do is I'm going to use it to find VIY. We actually had another problem that was similar to this, where we had the ball landing on top of the hill with the golf ball. We were actually using it to find VFY, but we can actually use this one to find VIY, because VFY is going to be 0. We're going to go to the very highest point, so this part will disappear. And so if I do that, then these two have to equal each other. And so to find VIY, we're actually just going to square root this stuff. Hey, this actually should look a little bit familiar. When we did Common Man, we actually used that to figure, now we launched him straight up, but we used that to figure out how fast he was going. We could have done this anytime we launched him to figure out how fast he was going, but it was easier when he was going straight up. So we're going to plug in to 9.8 and then how high this goes, and that should find VIY for me. I'm going to go ahead and calculate this. Handy dandy calculator. Whoops, got to get out of that. Don't need a periodic table. Square root 2 times 9.8 times 13.5. So I get 16.26653. It keeps going, but that's... Now the common mistake is people stop there. They're like, hey, I'm done. Circle it, I'm done. But what you've actually found is just how fast vertically they're throwing the ball. I want to know how fast diagonally. So I'm trying to go after VI itself. Now is where the angle is going to become important, because we know that VIY can be found by taking my VI and multiplying by the sine of my angle. We've been using it to find VIY. Now what we're going to do is we're going to use it to find VI. So if I divide by the sine of the angle on both sides, by sine, hello VI. So just a little bit different. We're dividing by that sign. We should get a number larger than that. How do I know it's going to be larger than that? Because the sine of every single angle always has to be less than 1. And if I divide by something less than 1, I get a bigger number. Same thing's going to happen in problem number 70. 70, you have this skier. They're coming down. If you've watched them on that giant slope, and then at the end, they basically take off, and we measure how high they go. So they're doing some kind of distance, or they're actually looking for height off of that thing. So again, in that one, they come down that giant hill, they hit the ramp, they take off at a certain angle, they go up a certain height, and we're going to try to figure out how fast they have to come off that thing to hit a certain height. So again, they give you a height and then use that to find it. I think this one is kind of neat because we don't actually use anything horizontally. Everything's kind of vertical and just kind of a reverse of finding it. Now that I know VI, I could ask other questions like how far away the wall should be, how much time does it take to get to the top, but then those are just same as we've had before. So this is the only part that's kind of new. Ta-da! No little problem. We're zipping along. It's only 9 o'clock. Awesome. Last one. This one's a really weird problem. It was another projectile problem in the book, so I grabbed it. I just thought it was kind of an unusual one. It doesn't really fit into any particular category. The idea is this spider is crawling across the table, and then it jumps onto a magazine. Why, I don't know, but that's the idea. And in this problem, they give you the initial velocity, so they do actually give you VI, and they give you the angle, so it's very similar to the earlier stuff. And it lands on this magazine 0.077 seconds after it left the table. So in other words, they give us the time that it actually takes to land on it, and we're trying to figure out how thick the magazine is. So I'm going to grab some of that information. 0.87, 35, 0.077. I'm just writing those down so I don't forget them. Spider. There you go. There's my spider. So our spider is crawling along the table. Magazine gets in the way. So let's put a magazine over here. It might be a stack of magazines. So here's some magazines. Let's put another little magazine on here. They look like books. It's okay. One's a little bit thinner. So what they're going to do is they're basically going to jump. They're going to launch themselves with a certain velocity at an angle. I just put them sideways so you can see the spider. It's probably going straight. I guess some spiders do actually kind of walk sideways and maybe jump sideways. But so it's some kind of jumping spider. Takes off at this velocity. So this is our VI. And it takes off at this angle. So this is our theta. Now, I don't actually know how they land on the magazines, and we're going to actually find it doesn't matter. In other words, they might jump up in the air and then come down and land on the magazines like this, or they might be so close to the magazines that they basically go straight to the magazine. So another situation might be that the spider is here. There's way too many legs, but that's okay. So maybe the magazines are really close, and so it just goes boom straight up to the top, and so it doesn't actually have a time to come down. I usually think of this first situation, but it could be the second situation. The nice thing is it won't matter. It'll be solved exactly the same way, give us the same answer. They want to know the thickness of the magazines. So thickness to me in this particular problem is I want to know how high they jump. I want to know this. I want to know why. I want to know why they jump. That's one I'm not going to answer, but I kind of am going to answer in this problem. Sorry, bad joke. If I do this and I kind of go after it, obviously if I'm going to find y, I need to know something about VIY, so I'm going to kind of go after what we've been doing. Let's break this up into VIY. I could break it up into VX, but I don't think I need that, so I'm not going to put it on there. But normally I would tell you to find VIY and VX. For this one, I'm just going to find VIY. So if I do that, that's going to be my VI, my 0.87, times the sine of 35 degrees. Hand it into calculator. So I get 0.499. So this is how fast vertically they're going up, about half a meter per second. So I'm after y, and I have VIY, but the other thing that's interesting in this one is I also know time. So you have to kind of watch your units. So a lot of people kind of skip over that. They think we haven't had time given to us. We've always had to find time, or we're given some kind of displacement. So they accidentally do that. If I'm going to go after y and I know time, it seems like I should probably use one of the equations that has that in it and not actually that last one like we've been doing. So I come back to my equations. My first instinct is I would love to use this equation. But for that, I need VFY. And I don't want you to make the assumption. I always get people who are like, can't I just make it 0? Isn't it at the highest point? Well, probably not. He's probably gone past his highest point and he dropped down onto the magazines. Plus, this doesn't have y in it. It wouldn't do me any good. So I'm not going to use that one. The next one is a possibility. It solves for y, but it needs VFY. This is a common one that people want to use because we've been using VFY of 0 so much that they want to use VIY, the time, with VFY of 0. I don't want to do this because I don't know if they're at their highest point or if they've come past it or if they're still on their rise. So I can't make the assumption that they jump and they're at the highest point for that magazine. So don't use this one. I think the better one to use is actually this third one because it finds y. I know VIY because I just calculated it. I know the time it was given me in the problem, and I know g because I've got my 9.8 meters per second squared. I'm not going to use this version of it because VIY doesn't equal 0. We're going to use the full version that's right in there. So we're going to actually solve for y by finding my VIY multiplied by t. So I've got those two quantities. I'll multiply them together, and then I'm going to subtract 1/2 of gravity multiplied by my time squared. So in other words, what we're going to do is we're going to figure out how far they should have gone based off of their initial velocity, and then how much does gravity pull them down to figure out the thickness. Boom. And that'll find why he jumped onto the magazine. So very neat little problem. It's probably the reason why they threw it in there, just something a little bit different. We had time. Time is always very useful, and it helps us out. Like I said, this is why I like to draw my pictures. I want to kind of make sure that we understand I don't necessarily know if I'm at the highest point. I would assume that he's jumped up and then landed on top of it, because if I think of I jump on something, I'm usually jumping higher than it and then kind of fall down. I don't usually have that be my highest point. So I doubt if that's probably the case. Ta-da! That's all of them. So theoretically, if you haven't finished these up, by the time you finish these up sometime tonight, then you've got them already. If you understand these projectile problems, you will be ready for at least 2 of them on the test. The other one is going to be a horizontal projectile problem, which you can still do the same way, but I might go back and look at some of your horizontal projectile problems that we did a while ago. I turned those back to you already, probably just because it's been a while. So it's a good one to kind of review. Other than that, it's going to start off with multiple choice. It'll have 6 multiple choice. A couple of them will deal with projectile motion and things like simultaneous fall. A couple of them dealing with relative motion. So those are all good ones to kind of look at. Usually I try to keep the calculation to a minimum on those, but the relative motion will require a little bit of calculating, and then 3 little problems. Boom, boom, boom. So that's our plan. I am done. I'm going to let you have the rest of the time to just relax, or if you want to continue to work on these, or if you have something else to work on, I'm good.